So today's lesson is on patterns in proportional relationships, block 6 from topic 3, and it's on page 89 in your math book. And what this does is this takes the situation that we did in the prior lesson about the fish pond, but this time, instead of surrounding the fish pond with tiles, we're talking about a different sort of material to surround it. So right here it says customers often prefer to have a fence surrounding the pond rather than tiles because they don't want kids falling in. So we're going to investigate the relationship between the side length of a pond and the number of feet of fencing required to surround the pond. So what you need to understand here is that the amount of fencing that fence is right up next to the edge of the pond. There's no buffer zone. It's just right there. So you've got pond, and then immediately right outside the pond is fence. So that's what we're looking at. And that's why I included this small diagram of what a pond with the fence around it might look like. So what they're asking us to do on this one is to create a table, a graph, and an algebraic rule to represent the relationship of pond side length, represented by the letter S, the variable S, to the amount of fencing, represented by the letter F. So you can see we've got our table here. And the one side is the side length of the pond, represented by the variable S, and the amount of fencing that would be required to surround that pond. So to get started with this, let's get started with this. I'm going to enlarge this just a tad to make it easier to do the work. Okay. So if the pond has a side length of, let's say, 4 feet. Oops, got to change it to drawing. 4 feet. How much fencing would we need? Well, remember, the pond is square, so that means we would have 4 feet on each side. So how much fencing would be required? Well, 4 plus 4 plus 4 plus 4 is 16. Okay. Let's go a little bit smaller. How about 3 feet per side? Well, let's see, 3 feet per side. Then this would no longer be 4 and 4 and 4 and 4. It would be 3 and 3 and 3 and 3. So 3 plus 3 plus 3 plus 3 would be 12. Right? I don't think I'm mistaken there. And what if, let's just say, we went even smaller, down to 2? How much fence would it require? Da-da-da. I bet you can figure it out before I even say anything. Right? 2 and 2 and 2 and 2. How much fencing would that require? Well, 2 plus 2 plus 2 plus 2. It's going to be 8. Correct? Of course. Now let's go the other direction. Let's go bigger. How about 5? 5 feet for the side length, right? I'm not even going to do the drawing on this one. I think you got this. 5 plus 5 plus 5 plus 5 would be 20. And how about, let's jump. Let's go huge, right? Let's go to 10. 10 feet on a side. That would be 10 plus 10 plus 10 plus 10, or 10 times 4. Of course, that's going to be 40. Yeah, I see that in the chat. Thank you. You're absolutely right. Okay, so we've already taken care of the table. Look at that. We've got the table. Now let's graph this. Okay, so let's graph it. I'll change the size of my dot to be a little bit bigger here. And so let's see. For 4 feet, we're going to have 16 feet of fencing. So go up by 4, 8, 12, 16. Looks like it's going to be right there. I think I better use my mouse for this one. Where is my mouse? There we are. Okay. And 3 feet would be 12. So here's 3 feet up to 12. Boom. All right. 2 feet would be 8. So 4, 8. Right there. 5 feet for the side length would be 20. And 10 feet, jumping clear to 10, 10 feet is going to be 40. So we have to go clear up to, there's 36. And 4 more would be 40 right there. All right, cool. So we've got, well, technically this is a scatter plot, you know, and I don't like this dot here. I'm going to clean that one up. There we go. Oh, that's way better. Now, let's connect our dots to see if we can determine whether or not, let's see how this is going to look. Oh, what am I doing? That wasn't right. I want to do that with a line. There we go. So I'll start at this one. Whoa, that definitely did not start at that. Try that one more time. Why? That's frustrating. Okay, we're going to try this one more time, only without the mouse. It did it again. I can't believe it.
You have to aim a little lower.
And I kept trying, but we're going to have to call that good. You're going to have to imagine that line goes all the way through those dots all the way. Okay. Use your imagination. It's easier on paper, obviously, because you can just use a pencil and a ruler and line them up. So with that being done, we've got our table, we've got our graph, but now we need to come up with our algebraic rule. Okay. So now, usually this would be our Y column and this would be our X column. But in this case now we're using F and S. So with here, F is going to equal how much, right? Let me move this. Sorry about that. Let me move that. So if this is S, then what's our algebraic rule going to be? What's going to go here if this is S? Hopefully you can see that it's going to be 4 times S to make F. So our algebraic rule is F, the amount of fencing that is needed is 4 multiplied by the length of the side. Okay, so let me zoom back out because we don't need it that big now. All right, so we've got our table, we've got our graph, we've got our algebraic rule for the fence pond scenario. Is this relationship between the side length and the fencing needed proportional? Now, hopefully, when you're looking at this, you're going, yeah, it is definitely proportional. And even better than that, you'll be able to tell me why for several different reasons, right? How do we know it's proportional? Well, one thing's for certain. If you look at the graph, you can see that that is a straight line, and that straight line passes through the origin right here at 0, 0. That alone is enough to tell you it's proportional. But just in case it wasn't enough, if you look at the table, F divided by S, every time you get the same amount every time. You get the same quotient. 16 divided by 4, 12 divided by 3, 8 divided by 2, 20 divided by 5, 40 divided by 10. F divided by S is 4 every time, every time. So you know there's a constant of proportionality. And then the other thing is if you look at this, if you look at the algebraic rule, which we can see right here, there's nothing added to the 4s, because if there was something added or subtracted to the 4s, you would know that that would not be proportional, but there isn't anything added. So it's proportional because we have a constant of proportionality from the table. It goes through the origin and it's a straight line on the graph, and there's nothing being added to the equation after the 4s. You simply multiply 4 times the side length. All right, well, let's move on to the next question then. All right, so now question number 3 says, if you found a proportional relationship, which we did, we are going to identify the constant of proportionality using each of the representations and explain how we found it. Okay, well, we've got this, right? I'm going to have to zoom in again to make life easier. So first of all, from our table, when we divide, well, we got this, right? Oh, that's not what I wanted. 4 divided by 1 is 4. 8 divided by 2 is 4. 12 divided by 3 is 4. It's amazing. 16 divided by 4 is 4. So here, we know what the constant of proportionality is, because F divided by S is 4 every time. The constant of proportionality. It's there. Okay. How do we find the constant of proportionality in the graph? How do we find it? If we go to look at the graph, how do we find the constant of proportionality? Let's scroll back up and look. Okay, here's our graph. Where's the constant of proportionality? Well, remember it's here. When x is, let me change the marker color. When x is 1, you go up to the line, you go over, look, there's the constant of proportionality. When x is 1, y is the constant of proportionality. I'm going to say that again. When x is 1, y is the constant of proportionality on a graph. So when x equals 1, y is the COP, as in 1 comma COP, an ordered pair on the graph. And then how do we do this from the algebraic rule? How do we find the constant of proportionality? But just by looking at the algebraic rule. Remember the algebraic rule? Y equals, oops, sorry about that. My bad. It's not Y. F equals 4S. In the algebraic rule, your constant of proportionality is the coefficient of your input variable. And in this case, your input variable is the side length of S. So the coefficient of the input variable, coefficient, is 4. Remember, a coefficient is the number that is multiplied by a variable. And in this case, so you should be able to, after today, you should be able to look at an algebraic rule, otherwise known as an equation, a linear equation, or a graph, or a table, and be able to identify the constant of proportionality in each and every one of those. If you can't, it's only because you haven't been listening and paying attention. There's no reason for that. Okay. Zooming back out. Moving on to the next question. Ooh, and we don't have time to answer this next question because it is sort of a long one. But I'm going to challenge you to do your best to complete question number 4 before tomorrow, before our next lesson. Complete the statements to show that what you have learned about proportional relationships. Now, the word bank choices, you have constant proportionality, origin, line, rate of change, intercept, and ratios. Now, of course, to know where to put all of those, you're going to have to know what they mean. So make sure you brush up on the definitions of those and how they're related to this paragraph right here. Okay. Well, that's my time. I'm going to stop the recording for now